Welcome to the advanced section led by our amazing TF, Prahlad. He's going to talk about this four-color theorem, which I briefly mentioned in the first lecture of mathematical modules, but Prahlad will dive into much more detail and also talk about a little bit interesting developments in the recently. Yeah. Okay, so Prahlad, is your stage.
Yeah. Okay. Thanks, everyone. Thanks, Chi-Ning, for the introduction. So, yeah, in this talk, we're going to look at the four-color theorem. So, we divide this talk into four parts. And at the end of each section, I have a question slide saying that the number of participants is not too high. I think we'll just stick to Zoom. And you can type in your questions, and at the end of each section, I'll look at the chat. So the first section, we'll just talk briefly about the history of the problem. The second section is going to be a little bit mathematical. If you're not very comfortable, it's okay. Just look at it, get a brief overview of things. And the third section is not as mathematical, and the fourth section is mostly philosophical and historical. So that out of the way, let's get started and let's go into the problem itself. Right. So what we have is this map. Okay, we'll call this map is of a country, some fictional country. Let's say we call it Blobland. And our goal is as follows: that we want to color its states so that no two neighboring states get the same color. So Chi-Ning briefly mentioned this in his talk, but I'm just repeating it again for the sake of completion. So why do we want to do this? Mostly aesthetics. It looks better, if no two neighboring states get the same color, so that people don't get them. So there's an obvious way to do this, right? So this country had 10 states, and if you just color each state by its own color, then no two neighboring states will get the same color. So, but we ask if we can do better, and the answer turns out to be yes. And it's actually not very hard to see why as well. So, for example, the purple state at the bottom right corner, this guy here, you can color it light blue, right? And you'll still be okay. Because the other light blue colored state is far away. So we once again ask if we can do better. And the answer turns out to be yes. So we'll do this in a slightly algorithmic way. Even though there's probably an easier way to do this, this is just helpful, to get us, started thinking slightly computation. So what we do is consider the state which has the most number of neighbors. So this guy here has 6 neighbors. You can check that out. And you can also check that this is indeed the most number of neighbors the state in Blobland has. Now, what we do is color all of its neighbors using different colors. So in total, we've used 7 colors so far, right? One for the state itself, the brown state, and 6 other colors. So now look at the uncolored states. So if you look at these bottom 2 states, these are neighbors of this blue vertex. The blue state. And these are uncolored. Now look at how many colors I've used in its neighbors and itself. Right? I've used 1 here and 3 already. So I have to use 6 in total, or at most 6 in total, to color the blue state and its neighboring state. Note that I have 7 colors with me. Therefore, there exists 2 other colors which I have not used so far, right? And therefore, I can just use them. Okay, I just color them with pink and light green. Now you can do the same thing for the uncolored state, which is a neighbor of this light yellow state. Just color it with 1 color that is not being used by any of its neighbors, right? Any of the yellow's neighbors. And I can do this because we've colored, we've used as many colors as there is in the maximum neighboring, or the state which has the maximum neighbor. And therefore I can color this. So I've colored Blobland now with 7 colors. So we ask again, right? We agreed. We want to see if we can do better. And what we do now is just get this a little bit formalized. So let D of S be the number of neighbors state S. So why am I using this notation will become clearer a little bit further into the talk. Now let this capital delta, so this is the Greek letter capital delta, of this map M be the maximum number of neighbors a state has, right? Then what have we done? To color Blobland, we colored the map with delta of M plus 1 many color, right? And it's not hard to see that you can do this given any map. So we ask again, right? Can we actually do better? And this is where the 4 color theorem starts. Okay, so let's go into a little bit of history. Now, in 1852, Francis Gauthray, I hope so all of these names, I hope I'm pronouncing right. If I murder the pronunciation of any of them, I'm very sorry. So please let me know in the chat if I'm terrible at this. So anyway, so in 1852, there's this British cartographer who later became a lawyer and a botanist, who postulated that 4 colors are sufficient to color any map, right? However big a map you give me, I will just require 4 colors to color them properly. Now, this is a crazy result if you think about it, right? It doesn't matter how many states this country has, I can always color it with just 4 colors. Now, as I said, he went on to actually become a lawyer, and he moved to South Africa from Britain, and I think he was instrumental in setting up a fairly big university there. Anyway, he moved on from CS and math. That's what's important to us. His brother, however, Frederick, he posed this question to Augustus De Morgan. So De Morgan is a huge figure in logic and math. You might have heard of De Morgan's laws, and also you might have heard that he was the one who formalized mathematical induction. If you haven't heard these terms, it's okay. We will actually use mathematical induction later. So it's just a homage to him, I guess. So De Morgan couldn't solve it, and he shared this problem with William Hamilton. Hamilton, again, huge figure in British mathematics. He was the one who started quaternion. That's a little bit of group theory used a lot in physics and quantum mechanics. Anyway, so he wrote this letter on the right, essentially saying that I have no idea, this looks very obvious, I don't know why I can't solve it. He actually goes on to say that, if there's an obvious solution, and I'll commit suicide or something like that. So anyway, so William Hamilton too couldn't solve it. And therefore it became a conjecture, which just means that people believe it's true, but they can't prove it. And the conjecture is that follows that 4 colors are sufficient to color any map, right? So after 2 decades, Arthur Cayley, another huge figure in British mathematics, if you've heard of the Cayley-Hamilton theorem, or if you've done any group theory at all, you would have come across his work. And he revived the search for this proof, right? He couldn't solve it as well. His student, though, his postdoc, I think his PhD student, doctoral student, Alfred Kemp, again, I think I'm saying the name right. He published a proof of this conjecture in Nature the following year, right? So 25 years, the problem was there, and sorry, can you hear me? Did you lose me in the middle?
Yeah, we lose you a little bit, but now we can hear you.
Okay, I got a call. My bad. Anyway, so okay. So what were I saying? Oops. So his student solved it, Alfred Kemp, and because it was a 25-year-old problem, he got a lot of laurel. So he he went on to I think become a member of the Royal Society, and I think he was even knighted. And right, so then, as with most problems regarding maps posted by British people, the problem didn't end there, right? So it went up. In 1890, Percy Hewood proved that Kempe's proof was incorrect. And this was a bombshell, right? It took 10 years to find the problem with the proof. And when they found it, everyone was obviously, taken aback. However, he salvaged enough of the proof uh, and proved that 5 colors are sufficient to color any. So what we will do is prove that 6 colors are sufficient, and we will, if we have time, sketch a proof of Hewood's theorem. So I think this is a good place to ask any questions. So if you have any, please let me know. So, right. So there's a question regarding, if this covers only real world maps or so on. Note that I've actually not defined what a map is, and this is by design, because the definition of a map is not very obvious. So as Chi-Ning replied, it actually requires some work. And that is exactly what we'll do now. There are no more questions, we'll move on. Okay, great. There aren't any more questions. So the actual conjecture is stated for something called planar graph. Oh no, 1 second. Okay, great. So, and that is what we'll look at now. Okay, so consider our favorite country again, Blobland. And now what we'll do is consider the capital city of each of the states, right? And depending on the neighbor, the adjacency or the neighboring states that one particular state has, we want that the capital of the country to be connected to them, right? So this is what we get if you do the thing. Now, just to put it in different places, if this is the country, we have corresponding map. Now, note that any coloring of the country corresponds to coloring of this graph. So again, Chi-Ning briefly mentioned what a graph is, but for the purposes of this talk, just think of graphs as a bunch of points connected by a bunch of lines, right? That's all a graph is for the purposes of this talk. Now, again, note that a coloring of this map of Blobland corresponds to a coloring of this corresponding map, corresponding graph. And yeah, here's another example of the coloring. Okay, so graphs which can be constructed from maps are called planar. This is not entirely true, but it's just for us to get a feel of it. So here's another example of a map and the corresponding planar. Note that as the maps get more complicated, the graphs also get more complicated. So equivalently, graphs where the vertices are drawn on the plane and the edges do not cross each other are called planar. There's a footnote here in that I have to prove many things. The first thing is that, okay, I said some statement before and then I'm saying this statement is equivalent. You should, or you might ask why this is true. The answer is one, not very obvious, because I have not defined what a map is. And it's also not the proof is non-trivial. So I'm not going to go there. Hopefully, I just want you to get a big sense of it, right? So, but again, so I also have to tell you what I mean by drawn on the plane and edges not cross each other. So I'll briefly mention this. If this goes over your head, it's okay. So take a look at this graph, right? Here the edges cross each other. However, I can draw this so that the edges don't cross each other, right? So what the actual definition is that a graph where there exists a drawing of the vertices and edges, where the edges don't cross each other, then these graphs are called plane. So note that this corresponds to a map, and this map, actually you can show that 4 colors are needed, right? It is required that there are 4 colors to color this map. So anyway, so you also have to note that not all graphs are planar. Here's an example. You should once again ask me, okay, why is this not planar? How do I know that there exists no drawing of it which it becomes planar? For which I will tell you that I'm not going to prove it now, because the proof is once again fairly actually highly non-trivial, because it uses, well, if you want to prove it from first principle, it uses some stuff from algebraic geometry and so on. Anyway, so there are things that are non-planar, and but planar graphs are rich in the sense that they have a lot of properties. Let's look at one such property, which is something called Euler's formula. Now, Euler, once again, a huge name in math. I'm not going to actually state Euler's formula, but what I'm going to do is state one of its corollaries, which is actually easier to look at based on what we have so far. The corollary is as follows: that if G is a planar graph, then the number of edges is bounded above by this number, 3 times the number of vertices minus 6. Now, note that in general, the number of edges can be quadratic in terms of the number of vertices, right? It can be something like v into v minus 1 by 2. It can be at most that. But in planar graphs, what Euler's theorem kind of implies is that the number of edges is at most linear in the number of vertices. So if we look at these two graphs that we have here, then just look at the number of vertices, right? In the left, which corresponded to Blobland, if you remember, the number of vertices is 10 and the number of edges is 9. So if you plug in these things, so 19 is less than 30 minus 6, obviously. And if you look at the one on the right, the number of vertices is 4 and the number of edges is 3. And if you plug this in, you get 6 is less than or equal to 3 times 4, which is 12 minus 6. So this is, you get 6 is less than or equal to 6. Therefore, this is also tight, right? In the sense that there exists a graph where there is an equality here. Anyway, so in a graph, we let, for a vertex V of the graph, we let D of V denote the number of vertices adjacent to this vertex, which is also the number of edges that come out of this vertex. So in this example, D of V is equal to 6, right? You can probably see that this is equivalent to the degree or the thing that I described for the state. And this is actually exactly why I called it D of S in that case. Anyway, so we let delta bar of a graph, of a planar graph, no, any graph, G, to be equal to the total number of degrees, the sum of the degrees divided by the total number of vertices. Right? This is how you normally define an average of a bunch of things, right? And this is the average degree of the graph G. In this, you can check that for graph, this one, G1, the average degree is this, 3.8, which I've just written as 2 into 19 by 10. And in this, I can write the average degree is 3, right? Why? Because everything has actually three vertices, three edges coming out of that. Therefore, the average is obviously 3. So, why have I written it this weird way, right? Because of this. This is an observation which is not very hard to see, but if you can't see it, just take the result. So, the observation is that the sum of the degrees of the vertices is actually equal to 2 times the number of edges in a graph. One way to think of this is that if you look at what is the degree of a vertex counting, it is counting the number of edges that are coming out of this vertex, right? Now look at it from the edges point of view. Each edge is counted by 2 vertices because it has 2 endpoints, right? Therefore, it will be counted 2 times in the degree count that we have on the right. Therefore, this 2 times this number of edges is equal to the sum of the degrees of the vertices. If that went over your head, don't worry. But if you kind of got it, this is something that is used everywhere in math, right? Counting in 2 different ways. So anyway, what does this tell me? This tells me that the average degree, so this is the sum of the degree divided by the number of vertices, is just 2 times the ratio between the number of edges and the number of vertices. Okay, you should ask me why you care. You should care because of this very weird or very surprising result. It says that if you have any planar graph, then there exists a vertex of this graph with degree at most 5. Okay. If that sounds weird to you and it sounds surprising, it is surprising. You should be weirded out a little at least. So let's look at this, right? What do we know? We know that the average degree is this 2 times the ratio of edges to vertices. And using the corollary that came from Euler's theorem, we can write 2 times the number of edges as this. So if you remember, the number of edges was bounded about by 3 times the number of vertices minus t. And therefore, this is this number, 6 times the number of vertices minus 12 by the number of vertices. And this is strictly less than 6, right? So here the number of vertices cancel out, minus you have some number, some small number. Therefore, it's strictly less than 6. So what does this mean? This means that the average degree is strictly less than 6. Since the average is strictly less than 6, that means that at least one vertex must have degree at most 5, or strictly less than 6, therefore at most 5. So hopefully you get the idea of this. Think of what would happen if you don't understand why this implication is true. Think of what would happen if everything had degree, at least 6. Then the average will be at least 6, right? So by a contradiction or a contrapositive thing, if you want to think of it that way, there must exist a vertex of degree at most 5, which proves what we were after. So what we'll do now is prove that 6 colors suffice, right? If you give me any map, then I will color with at most 6 colors. So take any map, call it n, and let G be the corresponding graph. So we will actually use induction on the number of vertices in this graph. If you don't understand what's happening now, it's okay. Anyway, so what do you need for induction? You need a base case. Base case is obvious, right? Take a map which has only one state, then the corresponding graph has only one vertex, which can obviously be colored with at most 6 colors. Just color it with one color. Favorite color, just color it. Okay, so the base case is done. So next we need the induction hypothesis. What is that? So our hypothesis is that for all graphs with k colors, with k vertices, our proposition is true. That is, it can be colored with 6 colors. Now take a graph, planar graph G, with k plus 1 many vertices. And what do we know? We know that by the previous theorem, there exists a vertex V with degree at most 5. Remove it, okay, from the graph. What is left is a graph G dash which has k many vertices. Moreover, you can at least hopefully kind of see that this is still planar, right? If I remove a vertex from a planar graph, everything else is still planar, right? Because I can draw it. Use the same drawing, just erase the vertex B. Now, what do we know? We know that G dash can be colored with 6 colors. That's our hypothesis. And if G dash can be colored with 6 colors, and this V has at most 5 many neighbors, each of them might get a different color or the same or similar colors. I don't care. It is just colored with at most 5 colors, right? It's neighbors. Therefore, there exists 6 color that I can use to color this vertex, right? Now that I've colored this vertex with the 6th color, I've colored G with at most 6 colors, right? I've given the vertex V a color, G dash already had a color. Therefore, putting things together, you have a coloring for G. So what have we done? We proved our induction step in the sense that assuming that we have, we can always color a map with k many vertices with 6 colors. I proved that you can always color a map or graph with k plus 1 many vertices with 6 colors. Therefore, by the principle of mathematical induction, which, as I said before, was formalized by De Morgan, we have that 6 colors suffice. So now note that this is, even though it's not as powerful as the 4-color theorem, it is still a crazy result, right? You can give me some crazy map, I will always be able to color it with 6 colors, right? This usual Crayola thing that you get in your convenience store, that's enough. Whatever crazy map you give me, I can color it with just the colors that you see with the crayon box. This is a good place for questions. So if there are any, I'll be happy to take. So I'll wait for a minute or so. Oh yeah, yeah. Chi-Ning mentions Kuratowski's theorem. That's once again a brilliant result in. Oh, okay. So what is the vertex with 6 neighbors? Oh yeah, cool. So what? Okay, just a second. So look at the look at this. What does it say? It says that there exists a vertex with degree at most 5, right? So therefore, the number of neighbors that V has, the thing that I'm removing, is has at most 5 neighbors. So it's colored with at most 5 colors. Therefore, I can use the 6th color to color the vertex. Hopefully that answers your question. So yeah, so what if there exists a vertex with 6 neighbors? Then I need at least 7. Yeah, so I'm not saying that all vertices in the planar graph have at most 6 neighbors. Sorry, at most 5 neighbors. I'm just saying that there exists a vertex. I can find a vertex with at most 5 neighbors, right? Now, I will remove this particular vertex. And I can do that because it exists. I will remove it, color everything else, right? I can color everything else because of the induction hypothesis. And I've colored everything else somehow, magically, right? Something has told me that I can color this with 6 colors. Now, if once I've colored this with 6 colors, I now have, I just need to color this vertex V, right? And since it has at most 5 neighbors, I can use an extra color that I've not used in these 5 to color this vertex. Is that okay? Hopefully that's fine. We haven't gotten a follow-up question yet. So if you do have, like, if anything's still not clear by the end of this talk, feel free to message me on Discord or just reach out to me in mail or anything. I'll be happy to clarify. Anyway, so let's move on, right? Now we look at key ideas to as what led to the 4-color theorem. This is most of the mathematics that we'll be doing. in this talk. Everything else is mostly intuitive stuff. Anyway, so let's go back to maps because I find them a little more intuitive. They look nicer, you can color them better and so on. So consider a planar graph. Then what did we prove? We proved that there exists a vertex with degree at most 5. What is this in the language of maps? If we have a map, then there exists a state with degree at most 5, or degree, or the number of neighbors of the state is at most 5. That's what this means. Now, what we'll define now, is something called unavoidable set. So what does this theorem say? This theorem says that every map must contain at least a state which looks like a monogon, by which I mean it has exactly one neighbor, a digon, which is something which has 2 neighbors, a triangle which has 3 neighbors, a square which has 4 neighbors, and a pentagon which has 5 neighbors. Right? That's what this theorem says. It says that whatever map you give me, at least one of these things must exist. Therefore, this set, a monogon, digon, triangle, square, and a pentagon, this is called an unavoidable set. And why do we care about them? We care about them because we will encounter them in every map, right? So Kemp, Cayley's doctoral student, he gave this as the unavoidable set. You actually don't care about monogons. You can care about just a digon. So here, this dotted line is just to say that we don't know what else is going on in the map, right? He just said that at least one of these 4 things must exist in a map, right? You must have a digon, triangle, square, or a pentagon in a map. And after this, a lot of people came up with a lot of unavoidable sets. So another important unavoidable set was Paul Wernicke, who said in addition to digon, triangle, and a square, he came up with this, right? Not a pentagon, but a pentagon and a pentagon, like a pentagon plus a pentagon, and a pentagon plus a hexagon, right? So he calls each of these things configurations, right? Because it's not just a state now. It can also be a bunch of states together. So he proved that this is also an unavoidable. The proof of this is actually not very hard, but I'm not going into it. Yes, it's not really important for the purpose of this talk. So a lot of people started producing unavoidable sets because, as I said, they were important. So in 1920, Philip Franklin, I think he was a PhD at MIT at the time, he produced an unavoidable set with 9 configurations. In 1940, 20 years later, Henry Lebesgue, I think I'm pronouncing his name right, name wrong. I think it's supposed to be Ohi Lebesgue, I think, but I'm sticking to Lebesgue. I'm sorry if there are any Germans in the audience. So anyway, he constructed several unavoidable sets. And Lebesgue, once again, a huge figure in math. If you've studied any analysis, you would have come across his work. Any physics, I think people use Lebesgue integrals all the time in physics as well. So anyway, huge figure in math. He also gave his shot at the 4-color theorem he couldn't do. And by 1960s, unavoidable sets with thousands of configurations were produced. So you can already see that things are getting, large, right? And this was the reason why computers became a thing. Anyway, so let's pivot and look at one more thing. And we look at this concept of minimal criminal, right? Oh, sorry, Lebesgue is French, my bad. Oh, okay. Sorry. Yes, sorry, my bad. Yeah, I hope I didn't cause a war or something. My bad. Lebesgue is French. My bad. I don't know what I did. Anyway, so now we look at this concept of minimal criminal. So assume that the 4-color theorem is false, right? What does it mean? That means that there exists a map which requires at least 5 colors. And because there exists such a map, there exists a map with the least amount of states, right? And let's say there are k many states in this minimal map. And this map is called a minimal criminal, right? Because it's the smallest map, it is a smallest map, which does not satisfy the 4-color proposition. What does this mean? This also means that every map with at most k minus 1 many, it should be states, my bad, not vertices, states, is 4-colorable, right? Because this is minimal, everything which is smaller than it must be 4-colorable. So what does it mean? So can a monogon appear in a minimal criminal, right? Let's say it does. What does it mean? Look at the map without the monogon. We know that this can be colored with 4 colors, right? By the observation that we made before. But if it can be colored with 4 colors, you can color the monogon with just something that is not used, right? Because it has only one neighbor. What about a diagon? So this is Blobland, if you remember. Can a diagon appear in a minimal criminal? Nope. Using the same thing that we said before. It has at most 2 neighbors. Just color it with the 3rd color. And also note, this is a 4 coloring of Blobland that we started with. Okay, we had a 7 coloring. Now we've got it down to 4. Anyway, so what about a triangle? Can it appear? Nope. Using the same arguments, it can't appear in minimal criminal. So monogons, diagons, and triangles can't appear in a minimal criminal. That's what we've shown. Kemp also proved that squares can't appear in a minimal criminal. Note that this is not obvious. Indeed, if you look at a square, it has 4 neighbors. All of them might be colored with different colors. Then we can't use the argument that we made currently, right? Just before. We can't use that argument. Just use it, color it with a color that is not used in this neighbor. We can't do that. So it requires some work, but it's actually not too bad. We can prove it. Kemp's arguments are not too crazy. Anyway, so such a state which can't appear in a minimal criminal is called a reducible configuration, right? Why is it a configuration? Because it can be an arrangement of states, like we saw in the unavoidable set. And are there more reducible configurations? The answer is yes, and a lot of people found it. One of the major figures was David Burkoff. David Burkoff, he's incidentally a Harvard alumni. He was a prof at Harvard as well. And I think he was a graduate student at Harvard. But when he developed this method to construct reducible configurations, I think he was in Princeton at the time. So, and in 1913, he developed a method to construct reducible configurations. And in 1920, Philip Franklin, we actually saw this guy before. He was a doctoral student at MIT. He used these ideas to prove that all maps which have at most 24 states is 4-colorable. So wait, you can ask, we were talking about this minimal criminal B. How did we come to this map with at most 24 states? Essentially, what he showed was there are complicated reducible configurations. I keep getting calls. Okay, sorry, can you hear me again?
Yes.
Okay, my bad. Sorry, guys. Anyway, so yeah, in 1920, Franklin used his ideas to prove that 24 states are 4-colorable by getting a complicated looking reducible configuration which used 24 states. Anyway, in 1938, Franklin increased this to 35 states. So we are getting there. So essentially by 1940s, if you wanted to produce a minimal criminal, you had to go to like 36 states, and maps are already looking complicated. So let's merge these two concepts, and then I think we'll have time for a question. So a set of configurations is unavoidable if every map contains them. And a configuration is reducible if it cannot appear in a minimal group. These don't look, in sync with each other, really. So why did I say both of these things at the same time? Well, what happens if you can construct an unavoidable set of reducible configurations? That is, essentially, if you can prove that any map you give me, there exists a reducible configuration in that map, then the four-color theorem is done, right? Because what does it prove? No map can be a minimal criminal, which means that there exists no minimal criminal, which means that the four-color theorem is true. Because what did we say before? If the four-color theorem was false, then there must exist a minimal criminal. But if we can produce an unavoidable set of reducible configurations, then there exists no minimal criminal, which implies that the four-color theorem must be true, right? If that went over your head, it's okay. Just know that these were the concepts that were used to prove the theorem. This is a good time for questions. If you have any, please let. Any suggested reading to prove that squares are reducible? Yes, I will. After I upload the slides, after I give the slides to Chi-Ning, I'll also have a corresponding doc which gives you a good, reading list of sorts. So I'll share.
Probably, Prahlad, you probably have like 7-8 minutes, left.
Okay, cool. So, right. So now, So now all that's left is I'm just going to be talking about history now. So should be okay. So so this search was first advocated by Heinrich Heesch. I think I'm saying the name right, in the 1940s. And his hunch was that these configurations would be small. Even though the configurations would be small, the size of the set would be very large. And while he was giving this lecture, one of the attendees was Wolfgang Haken. He's a huge figure in math, and he actually solved one of Hilbert's problems, and he gave a good shot at solving the Poincaré conjecture. He didn't do it, but he came very, very close. And 2 decades after attending this talk, he returned to this problem, right? And he was in University of Illinois at the time, and he invited Heesch over, who Heesch is German, and he invited him over to Illinois to try to solve the problem. And by this time, Heesch had solved thousands of reducible configurations, and with the help of one student, I think Carl Dur, hopefully I'm saying the name right, and a computer. This is where the computers arrive. He started checking if large configurations were reducible. And even though they were not able to do it because of computational limitations, so note that so this CDC 1604 was the best computer that they had, right? It could do 100,000 computations in a second. A mid-range smartphone can do 2.5 million today, right? So it's what, 250 times? Math is hard. I don't know. It's a large factor, weaker than what we have today. Anyway, they took a much bigger computer called CDC 6600 and tried to solve this with one Shimamoto. He was in I think Staten Island at the time. And 2 years they tried, and Shimamoto came up with a configuration with the theorem that if one particular configuration was reducible, then the 4-color problem was solved. Unfortunately, Carl's program showed that the configuration was not reduced. Now, Carl later found out that there was a bug with his program, right? And the initial things that he did might or might not have been wrong. It's not known if the bug led to this particular thing, because a lot of mathematicians believe that it was indeed reducible. They couldn't prove that it was not. But Carl's program said that it wasn't, and everyone was like, okay, maybe it wasn't. Then nobody knows if the bug actually led to essentially, the progress being halted again, right? And Haken wasn't very good with computers, so he stopped talking about this problem for a while. And when he was giving a talk, Kenneth Apple, who was an attendee to one of the lectures, said the following: that essentially, there's nothing that can't be solved with computers. It just takes time. So why don't we give this a shot? And that's what they did. I don't have too much time to go over too many things, but essentially they spent the next 6 years trying the luck with computers, and then they used a lot of rules to come up with unavoidable sets. It was a terrible, not terrible, it was a very involved case analysis, essentially, where they essentially check thousands of cases by hand, thousands more by computer. They use all things that they had. Haken's daughter, I think her name's from Dohotia, who checked for by hand 2000 odd configurations for reducible. And in 1976, they wrote this in Illinois chalkboard. Modulo careful checking, it seems that we've proven the four-color theorem. And they were in a short clock because there are a lot of people who were close as well. And Kenneth had to go somewhere on leave. So they only had a month to rewrite their preprint, and they did it, and they announced the result in 1976. And a year-long peer review process later, it was published in 77, right? Everyone's happy, kind of, sort of, ish, right? These were the two papers that essentially changed mathematics as we know. Why? Because of this, because the response was muted, right? You'd expect, 100-year-old problem was solved, everyone's ecstatic and, champagne's about. Nope. There were two groups, right? One who believed that the thousands of cases solved by a computer was errors, right? What if there's some error with a transistor somewhere, right? How do we know that computer did everything right? There was another group which were unconvinced that the 700 odd pages of hand calculations were errors, right? And when Haken's son, he was at that point a PhD in UC Berkeley, was giving a talk, he noticed that these two groups were correlated with age. The younger ones were unconvinced that the handwritten things were error-free. The older ones were unconvinced that the computer one was error-free. So when he was giving this talk, Haken's son, he said this, right? This is a watershed movement in the history of mathematics, right? He essentially remarked that we have to ask, what is a proof, right? Is this even a proof? And this started getting, things from philosophy. So one of the things was from Timoko. Again, I'm probably completely harassing his name. He was a Russian philosopher who asked about, who published this in the Journal of Philosophy. And, he was talking about the philosophical implications of the four-color theorem, or the proof of the four-color. So his notion of a proof was something that must be both convincing, right? Someone who reads it must get convinced, and must be surveyable, in that someone who reads it must be able to work out the details. Even though he was okay with the construction of the unavoidable set, he was okay with the proof being convincing, right? Everyone, the mathematicians are happy with it, kind of, and nobody could find the error. But he wasn't sure about survey, right? He And even that, he was okay with the construction of the unavoidable set because it was done by hand. Even though it was 700 odd pages, he was fine with it. But he was not okay with the reduction part, which used a lot of computing. And he feared that mathematics would become empirical. In his words, like physics. And he asked if can a proof be considered valid if it cannot be checked by hand. There are a lot of other people who weren't happy with this at all, right? One person was Ted Swart, who was I think he was a writer, mathematical writer, who said this, right? Okay, what have Kent and Apple done? They just said, okay, here is an unavoidable set of reducible configurations. Look at it. I'm not going to tell you why it exists. Here it is. You can check. And therefore, sorry, my bad. This was by someone else. Sorry. So this Ted Swart was he replied to Timoko, essentially saying that, oh, why is it okay if computers do if handwritten proofs are too long and nobody can check it anyway, but if computers do it, suddenly it's a problem. But he Ian Stewart was the one, what I said before, essentially saying that, okay, here they've been given an unavoidable set of reducible configurations. Why must this exist, right? Mathematicians search is for structure, some nicety, and that doesn't exist. Some people were a little more, forthcoming with their critique, essentially saying that all of this was shenanigans. Some computer nonsense was happening. What is this? So Apple himself admitted to the fact that this is not elegant. This is terrible mathematics. But then he went on to say that, oh, but it is what it is. And how much time do I have? Okay. 2 minutes. I'll finish in 2 minutes. Is that okay?
Yeah, sure.
Okay. So slowly there were few errors that were found in the proof. All of that were, it was done very quickly, right? They fixed stuff very, very quickly. In 1989, about 13 years after their 12 years after their initial publication, Hagen and Apple had the last word on the subject. They published a final book, which is, I think, 700 plus 700 pages of workings. And they published it, and that's it. No other word from them, right? They fixed all the errors. In 1994, Robertson and others published a proof of the theorem, which was much shorter, right? In the sense that the unavoidable set was smaller, and the rules used to construct it was also much smaller. The algorithm was much quicker as well. However, they use computers for both the parts. For the unavoidable set, checking the unavoidability as well as the reducibility. In 2004, Gomke, he's currently in, I think, Microsoft Research Canada. He used a proof checker, which currently, I'm not going into too much detail, but to prove that the four-color theorem was indeed valid. So, what does this all mean? Right? So, I'll just leave you with food for thought. I'll just leave it here. Let me not read it. So, it's in descending order of, as in it's starting from philosophical questions to going to very mathematical questions at the end. So, yeah, one thing I would leave here is take a look at these questions. If any of them seem interesting to you, please give it a shot and let me know. Let me know in Discord or anywhere. So in the, I don't know how much time I have left. I think a minute or so. So okay, I have 5 minutes for questions. But yeah, I'll stay back. If anyone has any questions, please let me know. thank you everyone for your time. Thanks, Chi-Ning, for the opportunity. It was a lot of fun preparing and giving this talk. So yeah, the floor is open to questions. Let me know if you have it.